So I've kind of informally walked through how DFS and BFS work. Now let's on some level, let's walk through how the complexity of these things can be conceptualized. So here's where the specific representation you choose for your graph really starts to matter. So we have two representations that we talk about in this class. We have adjacency matrix, and adjacency list. Okay? And the space requirement for each of these is different, right? The adjacency matrix, like I showed before, has a space requirement is equal to v squared, but I'll just write it in the asymptotic notation as well. It's asymptotically the size of the vertex set squared, or the number of vertices squared. And the adjacency list has some dependence on the size of the edge set, but it does not have quadratic dependence on the size of the vertex set. So we have v plus e. So the question is, in terms of time, how do BFS and DFS perform? Right. So now in time, and let's just begin by thinking about DFS. Well, one thing that we can say for sure is that DFS can't run any faster than the size of the representation. So why is that? Right, so I'll make this claim. I'll say that DFS must be at least as slow as the representation size. So DFS is big omega, right? At least as slow as, right? No faster than v squared, right? In other words, v squared is the best we could ever hope to do with DFS, and the size of the vertex set plus the size of the edge set is the best we could ever hope to do with big omega. So why is this? Well, DFS it's an algorithm that enumerates the entire graph. Okay, so to do that, it has to read the entire data structure, right? So at a minimum, at an absolute minimum, DFS can't ignore parts of the data structure, right? Can't ignore parts of either the adjacency matrix or the adjacency list. It has to actually check the entire thing to make sure it hasn't missed anything, right? And so this is true for BFS as well. So I'll write BFS and DFS together here, and the idea, the reason for this, and this is a critically important thing to notice. The reason for this is just we got to check everything. We can't leave parts of the data structure unchecked. So at the very least, we need to be writing down every single thing about the data structure. So this is because need to at least check entire data structure. Right? Or check every element of the representation. So the question is, can we argue that DFS and BFS are also no slower than these expressions here? And it turns out we can. So the question is, and this can be a little bit clearer, or at least it can help you to clarify a little bit if you look at the pseudocode. So I highly encourage you to go look at the pseudocode in the book, read the book's explanation for why this is the case as well. But I'll give you the informal flavor of it here. So the reason is, think about DFS. So in DFS, the basic operation involves interacting with a stack, right? We take vertices and we grab the vertex and we put it on the stack. So basic operation interact. I'll just call it stack interactions. Stack interaction. Right, and a stack is a really simple data structure, right? We don't have to do anything extra with the stack other than pushing and popping, right? It's just one thing to one thing kind of a deal. So the question is, do we do more than v squared stack interactions? And the answer is no, right? Every vertex gets pushed onto the stack once and popped off the stack once, right? So we absolutely do, we only do linearly many, right, v many stack interactions, right? So how many stack interactions do we have? Well, we have exactly v. Well, if we're going to be exact, we have 2 times v, right? 2 times v stack interactions, right? One push, one pop per stack, per vertex. Okay. Right, and so in order to read the graph, right, in order to process the fact that we've got a graph, we have to do at least this many operations just to read the data structure. But once we've read the data structure, we only do 2 times the number of vertices interactions with our stack. Okay, so DFS is no slower than v squared if it's an adjacency matrix, and it's no slower than this if it's an adjacency list. Right, there's no way around this piece. If we've represented the graph in an adjacency list form, we have to read the entire representation to do a graph search. But once we've done that, right, and if you abstractly think about doing that, about reading the representation as a separate kind of a thing, then we'll use our, we'll capture this slowdown there, and then we'll interact with the stack 2 times v times, which doesn't increase the order of complexity, right? So DFS is still going to be big O of v squared in the adjacency matrix, big O of v plus e in the adjacency list. Okay, so DFS is actually going to be big theta because it is both big omega and big O of the size of the representation. It's also going to be big theta, right? So DFS is in fact big theta of v squared, right? We know it can't be faster than v squared because that's the size of the representation. That's a trivial lower bound, and we also can show that it isn't any slower. Okay, so for both it'll be v plus e, and the same exact argument goes for BFS. Okay, so in BFS, what's the basic operation? Well, it's Q interactions. Q, again, is a linear data structure, and it costs constant time to NQ something, constant time to DQ something. And so then it's just the question is how many times do we NQ and we DQ? Well, we NQ and DQ every single vertex once, right? So what's our basic operation? Well, it's Q interactions. And again, we have exactly 2 times the size of the vertex set Q operations. So the same analysis says that BFS can't be any slower than V, than order V. Okay. So essentially in these, you can almost separate the processing the data structure or the representation of the input. You can almost separate that from the operation of the algorithm. And you can say as long as you don't make any bad choices in implementing your algorithm shouldn't need any more than linear in the number of vertices operations, and so there we have it. We have a nice what these end up being is we call them linear time algorithms because they run in time that is linear or proportional to the size of the representation. Okay. And so this is the first graph algorithms we'll look at. This is also some of the most informal treatment that I'll ever give a graph algorithm. And so, if you need more information, and I strongly encourage you to demand more information, go into the textbook and read the more detailed descriptions, and come to the synchronous session with your questions.